Good evening, everyone. This is Jamil Siddiqui helping you out tonight with your Fiveable AP Calculus Cram session. We've been having a little bit of technical difficulties. If you guys over in the chat could let me know I'm live and you can hear me okay, I'd appreciate that. We're going to get started tonight on calculus and tabular problems, so I hope this is going to work. We are going to forgo the slides this evening because that's part of the technical difficulties, but I will let you know that we have the Calculus Cram sessions every day, well, not every day, but Tuesday, Wednesdays, and Thursdays this week and next, helping you get ready for the AP exam. Today and tomorrow we are at 9 o'clock, and on Thursday we are at 7 o'clock. Tomorrow's session, Thursday's session will be at 7 p.m. The other two sessions will be at 9 p.m. So hopefully we'll see you there. The Fiveable Olympics are starting up at the beginning of May, so you should go to the Fiveable website and log in. You can earn prizes for studying for your AP exams. And as always, follow us at Think Fiveable for all of our social media. This evening, what we're going to be looking at is we're going to be looking at tabular questions on free response questions. And what that means is most of the time we're given a function like f of x equals something like x squared plus sine x plus 2 or something explicit, something that they tell us the rule. But on a lot of problems on the AP exam over the past years, they've started the problem by giving you a table of data. And you've got to perform calculus without having an actual function, but just doing it notationally and with the data table. So we're going to take a look at that because these problems have been very popular over the last couple of years. And a lot of people seem to think that this might be the type of problem that we'll be seeing this year. So we are going to just jump right in and start looking at some examples. So I'm going to try to share my screen here. Hopefully this works. All right, and now you guys should be able to see my tablet all right. We're going to jump right in here with this very first problem, okay? And a lot of times these problems like to combine different calculus topics in the same question. And that's why so many people kind of think we might be seeing this type of problem this year. As you guys know, our exam is reduced down to 2 questions this year. First question being a 25-minute question, the second question being a 15-minute question. They're going to have multiple parts, and the job of the AP exam writers this year is going to be how do you test the entire year worth of calculus in just 2 questions. So these questions seem to hit on a lot of different topics, and that's why we're going to be going over them tonight. It's good to see that a lot of you guys have come back. I'm going to do my best to take you through these tabular questions tonight, and then we'll take all of your questions, of course, and we'll go from there. So the first thing they like to do in these tabular questions is it's very, very, very common to see the word estimate, okay? And that's because you're not given the entire function. You're only given the function a couple of values. In this case, we only know 1, 2, 3, 4, 5 points where the function exists, okay? We do not have information really about the points in between other than what they tell us in the stem. So in this case, what they tell us, and you always want to read the stem because there are always clues in the stem. In this case, they're saying that the function is twice differentiable. Now, let me give you some advice on that. Anytime they tell you that your function is twice differentiable, they are telling you your function is also continuous and your derivative is continuous. And because of that, this opens up a whole realm of theorems that we're allowed to be using on the AP exam. So we're going to be looking at theorems a little bit tonight. We're going to have another follow-up session down the road. We're going to talk more about theorems, but you guys should know that you're responsible for the fundamental theorem of calculus, the intermediate value theorem, the extreme value theorem, and L'Hopital's rule as well. And these are the ones that you guys should know and know well. Okay, so again, mean value theorem, intermediate value theorem, extreme value theorem, and fundamental theorem of calculus. So when they tell you you're differentiable, that is giving you the green light that all the theorems work. So I don't know if that's going to show up in this problem or not, but if it does, we're allowed to use them because we've got the conditions for that. So in this first part, this is a very, very common question. You're asked to estimate the derivative. As you guys know, the calculus is all about finding derivatives, and in this problem, you're asked to estimate instead of actually find it. The reason it's an estimate is because we don't know the actual rule for f of x. So anytime you're asked to estimate a derivative, okay, anytime you're asked to estimate f prime of a value, that always means you're going to use a 2-point slope to do it. Every single time. 2-point slope. Some people call it an average rate of change. Okay, that is the direction we're heading in. That's what we're going to use. So in this case, we are asked to estimate the value f prime of 4. We've got to use a 2-point slope, and we want to use it closest to the value of 4. Here we have the value of 3 and the value of 5. So we're going to use these 2 points, and we're going to find the value, or estimate the value of f prime of 4. So the way you would write this is you'd start off by saying we're going to do f prime of 4. You would use an approximately equal to, and now you're just going to use a 2-point slope. So what I always like to do is I like to frame it by telling my reader what I'm doing. So I'm going to use f of 5 minus f of 3 over 5 minus 3. This by itself would not earn any points because you've actually got to apply it and use the table to earn the points. So from here, finding f of 5, you're going to get -2. Finding f of 3, you're going to get 4. And then you're over 5 minus 3. Again, I've been telling you guys this since we started working together. Don't simplify your answers. You don't need to simplify your answers. You can't get any more credit if you simplify your answers. You can leave it just like this, and you'll be completely correct, okay? Now, for those of you who can't resist and you have to, this is going to be -6 over 2, and that's going to take us to -3, okay? So in tabular problems, this is kind of the most basic, the simplest problem they can ask you to approximate a derivative by using a 2-point slope, okay? There was a question that came up, and I want to be clear about this. This evening's stream is A, B, B, C, or both. We are covering both tonight. Everything we do tonight is going to be appropriate for AB calculus or BC calculus, okay? So the second question I want to look at is another very common question they like to ask. And you'll notice in the first problem, they asked us to estimate a derivative. Well, in the second problem, they're asking us to estimate an integral. And these are the two biggest tools of AP calculus. So it's not surprising that they'd ask us to do this. So in this case, they're asking us to do a left Riemann sum. Okay, so I hope that you're all familiar with Riemann sums. Riemann sums are a way of using geometry to help us approximate the value of an integral. We're going from 2 to 13 in this problem, and it's of f of x dx. And we are using the subintervals indicated by the data, okay? Starting at 2, going all the way to 13, which means really what we're going to have is we're going to have one interval from 2 to 3, one from 3 to 5, one from 5 to 8, and one from 8 to 13. So what we're talking about here is we're really talking about putting together 4 rectangles. So what I like to do when I do this is I like to set it up. I know they're going to be rectangles, so I'm just going to write 4 times base times height. Because I know if I fill these in, I'll get the answer. So this is going to be base times height in each case. And what I like to do is I like to focus on my bases first, because my bases are the distance along the x-axis. So my first base is the distance from 2 to 3. So I'm going to get a base of 1 for that one. Okay. Then as I continue to go, I am going to go from 3 to 5. So that's going to give me a base of 2. So I'll put that in my second rectangle. My next one's from 5 to 8. So it's going to get me a base of 3. And then my last one is from 8 to 13. That's going to get me a base of 5. Okay. So once I've got the bases done, I now go back and I focus on how to get my heights. In this problem, they were really clear. They told you you're going to use a left Riemann sum. So when you're in rectangle number 1 goes from 2 to 3, okay? Basically, what you've got is you've got 2 heights to choose from. You've got the height of 1 and you've got the height of 4. But they told us to use the left-hand Riemann sum. That means I'm choosing between the left and the right height. I'm choosing the left one. I'm going to go, in this case, with the f of 2 value, which is 1. Okay? Then in my next rectangle, I'm choosing between 4 and -2. But again, they told me to go with my left height. I am going with that 4 value. In the next rectangle, I'm choosing between -2 and 3. The one that's on the left is -2. And in my last rectangle, I'm choosing between 3 and 6. So I'm choosing the one on the left, and that is 3. Okay? So this would be a final answer. Again, you don't need to simplify. This is perfectly okay. If you did go and you work this out, you would find out that this answer would be equal to 18, but there is no need to simplify this. So again, 2 of the most common questions they can ask you are approximated derivative, and that is always using a 2-point slope with the 2 points closest to the place they asked you to approximate. And then the second thing they're looking for is they're asking you to go and find a Riemann sum, and that is just using rectangles, okay? So pretty common questions, pretty straightforward. If you have any questions about either of these two, please put it up on the chat, and I'll be happy to answer any questions you have. But my assumption is that these are pretty straightforward. So now, from there, this has been a really common question over the last couple of years. And what's going on with this one is it's a combination of using the properties of integration along with your table. So let me explain what I mean by that. We're being asked to integrate from 2 to 13 3 minus f prime of x dx. And the first thing you should keep in mind is that when you integrate terms, you can separate them. So this one's kind of interesting because the first one is 3. I mean, we can mathematically integrate that. We have the tools to compute that answer. That is not a big deal for us to compute. We know exactly how to do it. Second one's a little more interesting because we've got f prime. And normally, we'd like to have the real function, the explicit function. But in this case, they're just giving us notation. Okay, so since it's notation, we've actually got to still integrate this, but we can't rely on all those shortcut integral rules you probably learned, like the power rule of x to the n, or the integral of sine, or something like that. So what I'd like to do is I'd like to break this up into 2 integrals, do them separately, and make sure everybody's comfortable with it. So this is going to be the same as just taking this problem and saying, let's integrate from 2 to 13 of 3 dx, and then let's subtract the integral of f prime of x dx from 2 to 13, and that 5 can actually be pulled out in front as a constant. Okay, so that is where we're going with this particular question. From here, 2 separate problems, okay? The first one, very straightforward, mechanical. You can do it. You can say that the integral of 3 dx is equal to 3x, and now you're just evaluating that from 2 to 13, and that will get you 3 times our first bound, our top bound, 3 times our bottom bound. So it's going to be 13 minus 2. Okay, so this is part of the answer right here. This is going to be part of our answer. The next place we're going to go is we're going to integrate f prime of x dx from 2 to 13. I caution you on this one because for this one, there's that -5, and the common thing is for students to forget that -5. So just make sure you bring that along with you, okay? And now this is a notational integral, and notational integrals are completely valid. So when you're doing this, you got to say, okay, who's the integral of f prime of x? And you're going to say notationally, that's just going to be the function f of x, because the derivative of f of x is f prime, so the integral of f prime has to be f. So once you've got that, don't forget your -5, and now bring your evaluation bar from 2 to 13. And what I like to do is I like to give my -5 a free ride all the way and just keep it on the outside as long as I can, because one of the common mistakes is to mix up negative signs. So just by keeping it all the way on the outside, now I can just evaluate f minus f, and I'm using 13 for my top bound, I'm using 2 for my second bound, and this is where the table comes back into play, okay? We need to now go to our table, and hopefully f of 13 is one of the values, hopefully f of 2 is one of the values. That is the case here, so we're going to get, this is equal to -5. F of 13 is given to us as 6, and f of 2 is given to us as 1. So the answer for this part is going to be -5 times 5. Okay, -5 times 5. So from here, you are completely good just combining your 2 answers. And again, I would strongly recommend not trying to simplify anything. There's our answer from the first one. Here's our answer from the, sorry about that. Here's our answer from the next one. And you can leave it just like that, okay? It's just like that. So I'm just going to take a real quick look at the chat to see how you guys are doing with these questions so far. The right Riemann sum, you were correct with that one. The question, do we formally show out our work with the antiderivative? Okay, now I think that you don't have to show these steps here, if that's what you're talking about. But I think it goes a long way to making sure you don't make any careless mistakes. Okay, so I would suggest to you to show the splitting up, because we really want to treat this as 2 separate integrals. At least that's the way I look at it. Okay. The last question, Cedra, I need just a little more feedback from you. We have to show the other step with the 3x and then the bracket was 0 to 2. So if you're talking about can you go straight from this integral to this answer, the answer is yes. You'd be okay with that. Okay, you'd be okay with that. But again, it would be from 2 to 13 instead of 0 to 2. Okay. All right, great. How you went from your answer that's squared to the rest. Cedra, I'm not seeing you on that, okay? So what I'm going to do for now is I'm going to say, just to make sure this is clear, I was integrating f prime of x here, and that's the integral I'm doing down here. And the integral of f prime of x is f of x. So that's how I got that answer, and that's how we use the fundamental theorem on this one. I want to jump down. I'm going to kind of jump around a little bit today because I want to kind of show you some similarities between different questions. So I actually want to jump down to this problem right here, okay? And you're going to see a similarity with this one. Oops. To the one we just saw. This is a brand new table, but again, it's asking you to do an integral based on that table. All right. So I'd like you guys just to take a minute. I'd like you to read it. I'm just going to be quiet for like a minute, maybe two. Give you a chance to think about this one. Then we're going to come back and discuss this one after you just saw the one that was done. So new table, new question. Take about a minute or two, and then I'll come back and we'll go over this one together. Okay. I saw there was a question to get the slides this evening. Again, part of the technical difficulties I'm having tonight is with the slides. I will be sure to post those with the replay. So if you're checking the replay out, you will get the slides with it when you see the replay. I apologize for that for this evening. But I'm just glad I'm with you all tonight live to make sure we can get some questions done this evening. So you'll see the slides afterwards. So I do want to discuss this problem. I really have a strong feeling that we might see something like this year. So I really want to make sure you guys are 100% comfortable with this. It's like the problem we just did, but there's a twist to it. And the twist is, in the last example, you're going to remember, we had to integrate f prime of x. And that notationally is very easy. The integral of f prime of x is simply f of x. In this problem, there's a twist. And the twist comes with the 2x. Okay, this is not a straightforward integral when you've got a 2x in there. Our notational integrals only work easily when our inside function is x. When you've got an inside function that's more complicated than x, that is where you've really got to be careful with your integration. So I don't know where you guys are and your comfort level on integration, but I'm going to make this statement. I hope it resonates with you. If you've got an inside function and you're trying to integrate, you'll want to think about U-substitution. Okay, that is where you want to go. The inside function being different than x, it usually is a U-substitution. So in this problem, the inside function is right here. It's at 2x. So when I go to integrate this, what I want to do is I want to try to set up a U-substitution problem. I want to go from 1 to 3 of f double prime of 2x dx. Okay, and I want to make sure that I do a substitution. U sub is the same as the reverse chain rule. So if you've heard it as the reverse chain rule, then U substitution is exactly that. Okay, so what I'm going to do is I'm going to set this up and make sure you guys are comfortable with the idea of U substitution. I want to make 2 points about this. One, the U substitution. The second point I want to make is I want to really get very, very specific as I label this. We usually just write from 1 to 3, and that's perfectly okay. But technically, we're saying when the x value is 1 and the x value is 3. Now, to me, that plays a role in this problem, and you're going to see why as we go through. So as I go to do this problem, the U substitution says we want U to equal the inside function. We want U to be 2x. And from there, we're going to find our du. And our du is the derivative of the other side, and that's 2 times 1. And then we write the dx on this side from the du over dx. At this point in time, what I want to do is I want to start bringing my pieces over into a u version of this integral. So I like to bring the integral over first, and we're just matching it up. It's all bookkeeping. So the first thing I do is I do that integral. And what I'm going to do is I'm actually going to outline it as I do it. So I'm going to bring that integral over first, and in comes the integral. Okay. The next thing I want to bring is this f double prime of something. And that can come right in, f double prime of something. But now's where the u substitution comes in. I now want to bring the 2x in, but I'm not allowed to use x's. I have to use u's. So that 2x has to come make a pit stop down here and say, how can I be rewritten? And it enters as 2x, but it leaves as u. So the 2x is replaced by that u. At this point in time, all I have left is dx. But again, I'm not allowed to have x's when I'm trying to write this in terms of u. So I go back down here where I've done my calculations, and I find out how can I figure out what dx is. And luckily for me, dx is right here in this equation. So if I solve this equation for dx, I'm going to find out that that's 1/2 du, which means in place of dx, I can write 1/2 on the outside and du here. And by rewriting it in terms of u, what I'm hoping now is a straightforward integral. Now, keep in mind at the beginning, we said when we've got just x as the inside, notationally, we can just integrate it the way it looks. What we've done is exactly that. We've made it so there's just a single independent variable. It's the integral of f double prime of u du. Now, the last thing that I like to do in these problems, and this is actually your choice. There's 2 ways to do this. So if you're used to doing it the other way, that's fine. But I like to bring my bounds in, okay? I want to say what happens when I bring x equals 3 over. And you might think, well, I just put the bound of 3 in. But that's not how it works. Because it's x equals 3, you have to take it down here, and you have to find out what u equals when x equals 3. So I see Nikki already ahead of me. And you're absolutely right, Nikki. When I put in 3 for x, u is going to equal 2 times 3, and that's going to give me u equals 6. So that bound on the top becomes u equals 6. And then when I go down this bottom one, and I want to figure out what u is, I know x equals 1, but when I bring that in, well, if x equals 1, then u equals 2 times 1, which is 2. That's going to give me u equals 2. The advantage of this is once I bring this into the u version, you can leave it there as u's. You don't have to bring it back as x's. Depending on how you were taught, you might have gone to u and then brought your answer back as x, okay? But you don't have to. So I prefer bringing the bounds in. Now I see, Akshita, I hope I'm pronouncing your name right. I see you got some confusion there. If you can give me a little more clarity about what's confusing you, whether it was the bounds or writing it in terms of u, I'll try to explain this a little bit more. But until I see that, I'm just going to kind of go on. So again, bounds, bringing in as u's, is that what you're asking me? How the u's work? Okay, again, the only things that got changed as u's are the 2x and the dx, because x's have to turn into u's. And by using my substitution rules, and my substitution rules, again, are in this box, 2x right here is going to change over to u. So where you saw 2x on the inside, I made it a u. Now the only thing left to bring over was that dx. So when I went down to the box, dx ended up equaling 1/2 du. Okay? And the reason the 1/2 goes out in the front is because in an integral, constant factors can be written in the front. You don't have to leave them on the inside. It's kind of a way to organize it so you're not cluttering the inside with constants. You saw me do that with the 5 on the last example. So from here, that constant ends up staying in the front, and now we're integrating f double prime of u du. Well, the integral of f double prime of u du is simply f prime of u, because we go backwards 1 from the second derivative to the first derivative. And now we're going to evaluate this from u equals 2 to u equals 6. Well, again, that 1/2 is going to stay out in front. And now we're going to get f prime of the top bound minus f prime of the bottom bound. So the top bound is 6, the bottom bound is 2, and this is where the table comes in. Okay, this is where the table comes in. So I'm going to finish this off, and then I'm going to take a look at the questions, and I'm going to go back and try to answer those questions for you guys. F prime of 6 is given in the table as 5. So I'm going to use f prime of 6 with a value of 5. And then I'm going to do f prime of 2. f prime of 2 has a value of -2. So this is going to be 5 minus -2. Okay? And I'm going to leave my answer just like this. Okay? I'm going to leave my answer just like this. Don't try to simplify it. It's not worth the chance of making a mistake. So I hope that is clear for everyone. I'm seeing a little bit of positive feedback. I appreciate that. I hope you guys are good with this. The thing I want to point out to you is be aware of U-substitution with these notational problems. You can do U-substitution with notational problems, and that's kind of not something you're used to seeing perhaps during the school year, but with a table problem that comes up pretty often. So I hope that is something that's making sense to people. Okay? Any questions on this so far? Are we good? All right. I'm going to back up. I'm going to take a look at another table problem with you guys. And I am going to go and look at this one this time. So on this one, you've got parts A, B, and C. I'm going to jump around a little bit, but I just want to point out something. I saw a question now. If you don't use U-substitution and you arrive at the same answer, would that be okay? The rule on the AP Calculus exam when it's being graded, if your math is correct, you get credit. Okay? If you've got good math, if you've got another method of doing it, and it's correct math, you can still do it. Someone mentioned the reverse chain rule. I used to have a student who could not do U-substitution very well, but they could guess and check the chain rule extremely quickly, which was kind of bizarre, but that's what they would do. That would be an acceptable way of doing this problem. You know, if you can do the chain rule, guess and check version that quickly, it's okay. So, Serene, the answer to your question is, as long as you're doing correct mathematics, you're going to get credit. Okay, they're just watching to see that you're doing the math correctly. So on this example, okay, I just want to point out one thing. I don't want to do this problem, but I want to show you. Look at this first problem. Look familiar? Okay, this is a different year. This is not the same year we've been looking at. And we've got a problem that's almost identical to the one we saw that we opened up with. Okay, so this idea of using an integral in a table problem is very, very, very common. All right, I'm not going to do that with you guys because it's so similar to the other one, but I just want to point out that they really like to ask that question. What I'd like you guys to do is take a minute and, well, we'll do it together, but look at question B, okay? Write the equation of a line tangent to the graph of f at the point where x equals 1, and then use this value to approximate f of 1.2. Here's what I want to point out about this. Notice the approximations again, okay? We don't have the exact function. We only have it at certain values. They love asking estimate and approximate questions with these tables. So I'm going to go and I'm going to focus on question B. We're going to bring that up right now. And I'd like you guys, again, I'm going to just give you maybe 2 minutes to get it started, and then I'm going to jump in and we're going to make sure you guys are comfortable with this, okay? So take about 2 minutes, start working it out, and then we'll touch base with each other. And that'll give me a chance just to scan the questions to make sure you guys are in good shape this evening. All right, so you see me highlighting this phrase, write the equation of a line tangent, okay? If we were having a full exam this year with all the questions and not a shortened version, I would promise you, you would see this phrase somewhere on the exam. Every year, this is one of the phrases that they use, okay? So what I want to make sure you do and what you understand is every single time you see this prompt, you should start by using point slope form of a line. And the way I like to write point slope form of a line, I like to write it like this because it just reminds me where I need to fill it in, okay? I know I need a y value to go here. I know I need a slope to go here. And I know I need my x value to go here. Now, for you guys who've been taking calculus all year long, you're going to recognize this as the x value is usually given, we call it the a value, To find the y value, we plug a into our function. That's going to be f of a. And then to find the slope, we're going to take the derivative and find it at a. So this is really the most common way of doing this problem. In this example, we're told that x equals 1. So we know our a value. So we're going to put 1 in right here. Okay. And now our job is to find f of 1 and then f prime of 1, because those are the other two blanks we need to fill in. Okay. The table gives us these values. So I go straight to the table. I look for f of 1. F of 1 is given to me right here. That's f of 1. So that's going to be -4. And then finding f prime of 1, right underneath it, f prime of 1 is going to be 5. So I take these two values, I substitute them in. I put 5 in for the slope. Careful with the negative signs on the -4, because that's going to be a negative, which is actually going to make it look positive. So it's going to be y plus 4 there. And I have now earned the first part of the points for this question, okay? Because they're going to give you a point or two just for getting the equation aligned. So now the second part. Use this approximation to approximate f of 1.2, all right? The way I would recommend you do that is I would say take that line equation you have and now solve it for y. So this is going to be y is equal to, and all I'm going to do is subtract 4. I'm going to put 4 on the other side, equals 5, equals, subtract 4, it's going to be plus 5 times x minus 1. So here's the deal. This is a linear approximation. We are saying that as long as x is close to 1, y is going to behave like f of x. Okay, so that's the whole idea behind linear approximation. So they're asking us to plug in 1.2. So we're going to say, hey, if that's the case, f of x is approximately equal to -4 plus 5 times x minus 1. And they're asking us to find f of 1.2. So that's going to be approximately equal to -4 plus 5 times 1.2 minus 1. Again, you can leave it. You don't have to go any further than this. You don't have to simplify this answer. You're perfectly okay just leaving it like this. And I'm going to stress that every single time because I'm working with my own students in my own class, and I'm watching kids get problems wrong because they're trying to simplify. So don't do it. It's not worth it. At this point in time, there is a follow-up question. Is this approximation greater than or less than the value of 1.2? Okay. Now, in order for you to understand this, you've got to understand a little bit about tangent lines and how they work. So we're going to go back. We're going to read the stem part of this question, and you're going to notice a couple of things. First thing, this function is differentiable. That's there for two reasons. That's there to say we're allowed to talk about f prime of x. There's never any problems with f prime of x. The other reason it's there is to tell us that our function is continuous, because if it's differentiable, it's automatically continuous. And again, what that means is if it shows up in part of the other problems, intermediate value theorem, mean value theorem, extreme value theorem are all at our disposal, okay? So then if you keep reading, you find that it just tells us we have the values of f and f prime. But if you keep reading, it gives you this random little fact, okay? The second derivative has the property so that the second derivative is always greater than 0. So what does that mean? And I see that actually over there on the side, you've already, you've already started to look at it, okay? So what that means is we've got again, it is always greater than 0. So if f double prime is always greater than 0, that means we have a concave up shape. And if our function is concave up, it is drawn like this, okay? That is the concave up shape. Now, wherever you go on that concave up shape, and you can go anywhere you want, when you draw a tangent line, it doesn't matter where you draw it, the tangent line is always below it. So here's a fact that you need to make sure you understand, that tangent lines lie below concave up functions. And the same is true, or the reverse is true. Tangent lines lie above concave down functions. Okay, so how does that help us? Well, we know our function is concave up. Therefore, our tangent line is going to lie below our function. If our tangent line lies below our function, our approximation is going to be an underestimate. So the way you would answer this question is you would write that we have an underestimate because f double prime of x is greater than 0. So the tangent line lies below f of x. If you write that, you get full credit. Okay, that's exactly what you're going to need to get this one done. So I hope that makes sense to everybody. Okay, so the idea of a tangent line and above or below. One more thing I'd like to talk about. This has not come up often. Okay, so I doubt we'll see it this year, but it goes in hand in hand with what we're saying. There's also something called a secant line. Okay, there are tangent lines and there are secant lines. Tangent lines touch at one point. So anytime you hear tangent line, you're thinking touching at one point. Secant lines are going to connect 2 points. So if you have a secant line to a concave up shape, that means you're going to have a point here and a point here. Secant lines always lie above a concave up shape. Okay, so secant lines always lie above a concave up shape. And likewise, secant lines lie below the concave down shape. Okay, again, that hasn't been tested too often, but I've got the picture up. They go hand in hand, so you can see the relationship between tangent lines and secant lines in this case. Okay, so I hope that question is clear for everyone. The next one I want to look at is part C. And again, I'd like to just give you a minute to read over it, and then we'll talk about it in just a second. Okay, so take a read on part C. All right, so in part C, there's a really big clue, okay? The AP exam is very consistent with its notation, and that can help you by giving you a clue. And the one place where they're giving you a clue on this one is right here by saying F, and it's F double prime, but it's F double prime of C equals some constant here, okay? F double prime of C equals some constant. So the place where we see the AP exam writing F prime of C over and over and over again, it's always written when they use the mean value theorem. Always written when they use the mean value theorem. Okay? What I tell my students is the following. If you're given a table and you're asked to find an exact value for F prime or for the derivative, that more times than not means mean value theorem, okay? Because that is the only way to connect points to a derivative directly. If you'll notice on the earlier question when they asked us about a derivative, we had to use an approximation. And that's because we have a table. Approximations is all we can do. The only time it's exact is by using the mean value theorem. So the one twist on this one is that it's F double prime instead of F prime. So what I'm going to do is I'm going to write down the mean value theorem in general, so you guys can all be reminded about it. And the mean value theorem says that the average rate of change is equal to the instantaneous rate of change. Okay, so the average rate of change for 2 points is f of b minus f of a over b minus a. And the instantaneous rate of change in some place is that derivative f prime. And they're going to say it's for c, where c is between a and b. Okay, so this is the mathematical way of writing the mean value theorem. But for any theorem, and this is important, for any theorem they ask you about in the AP exam, you must state the conditions first. If you do not state the conditions, you will not get full credit. Now, what do I mean by state the conditions? Okay, for the mean value theorem, you are not allowed to use it unless your function is differentiable, because it will not work if the function is not differentiable. So every time you're going to use a theorem, before you can use it, you have to say, because of this fact, I'm allowed to use it. So for the mean value theorem, it's because I am differentiable, I can use the mean value theorem. That has to be in your answer. The readers are going to be looking for that in your answer. If you leave it out, you're going to lose a point. You've got to state the condition. So as we're going through this one, okay, we need to now find out how the mean value theorem applies for this particular example. Well, in this case, we are ending up with the derivative, but we want to end up with the second derivative. Now, I saw someone in the chat has already mentioned it. The way we do it is we just use the second derivative here, but that means that these two have to become the derivative. So we can take the mean value theorem up another level by using it with the derivatives instead of the function. So now we've got all sorts of data on f prime. So they're telling us to do this, and they're giving us the values. They're telling us to do it from 0 to 0.5. So what we're going to do is we're going to say that f prime of 0.5 minus f prime of 0 all over 0.5 minus 0. And we're now going to compute this based on our table. And our table tells us that f prime of 0.5 is 3. F prime of 0 is 0. So we're going to get 3 minus 0 all divided by 0.5 minus 0, which is 0.5. Again, you could leave it, but if you do this out, you're going to find out that this is equal to 6. So what we're saying is that there is a value, r, because that's what they asked. They said, what does this have to equal? The value is that r has to equal 6 somewhere in this interval, guaranteed by the mean value theorem. Okay, guaranteed by the mean value theorem. So I hope that is clear for everyone here on this one. Okay, I see a question. Should we be specific to state continuous on closed interval and differentiable on open interval? Okay, that's not going to hurt you, but in the case of the mean value theorem, if you state differentiable, it is given that it's continuous. Okay, it's redundant. Okay, now if we were using a different theorem, if we were using the intermediate value theorem, let's say, now the condition of the intermediate value theorem is that you need a continuous function. In the prompt, if it says it's differentiable, it never said the word continuous. So in that case, you would definitely want to state that. You'd want to say, since the function is differentiable, we know it's continuous. Okay, so you just got to make sure you say the word that's directly tied to the theorem. Okay, so I hope that is clear for all you guys. I hope that makes sense. The next one I want to look at is this one. Okay, so again, there's a lot of words going on here. I don't want to read them. I'll give you a second to read it, and then we're going to talk about it. I see the question over on the side, and I appreciate what you're saying. We're doing Cram videos 3 nights a week. We're doing it today, tomorrow, and Thursday this week. We're doing it again next week, 3 nights a week, Tuesday, Wednesday, and Thursday. And then the following week, Monday, the day before the AP exam, we're going to have a 5-hour session. Okay. I won't be here for the whole session. I'll be taking about 2.5 hours of that 5-hour session, but there'll be a 5-hour session the date before the exam. So you guys will have 2 more nights this week, 3 nights next week, and 1 night the night before the exam. Okay. So as far as this problem goes, here we go. Okay. We're looking at, and I'm looking forward to seeing you guys for the rest of next week. This will be fun. As far as this question goes, we're looking and we're going to find what is the word that we really need to figure out to get things going. And here's some experience for you. Okay, this is where your experience has to kick in, and hopefully you've taken a lot of old AP style questions. And if you haven't, I strongly recommend that you do. Okay, for those of you guys who've been following me the last 2 weeks, I've given out my email. I'll put out my email again at the end of the session. If there is a topic that you are not strong at and you want practice problems, if you email me, I can get you some sample problems and you can practice those problems, okay? So I'm happy to point you in the right direction of old AP questions. Year after year, they use the same kinds of questions, the same kinds of prompts. The more you familiarize yourself with the old style AP questions, the better. So for any of you, and let me just do it now so I don't forget, for any of you who are interested in getting some extra practice problems, you can email me at jamil@fiveable.me, and I will be happy to set you up with some practice style questions, okay? So on this one, this is a piecewise function, and they're telling us now that g is given by this piecewise function, and it contains all the points that we see up above in f of x. So every point that f of x point goes through, this g of x function is going through. So the question is it possible that these are the same function? Okay, so here is where experience kicks in, all right? You've got a piecewise function here. And the one place where the AP exam loves piecewise functions is they love piecewise functions when they're talking about continuity and differentiability. And the reason they love it for continuity and differentiability is because if you go back and remember your definitions of continuity and differentiability, it's all about being able to approach from the left and being able to approach from the right. And the only functions where that really becomes an issue is in piecewise functions, because piecewise functions have the ability to have one rule on the left side and a completely different rule on the right side. So the idea here is we're told that our original function f, and this is where it's coming up again, is differentiable. And that means that if these are the same function, that g will have to be differentiable. Well, if g is differentiable, it first has to be continuous, and then we have to check differentiability. So I just want to review these two ideas with you guys, okay? The idea of continuity. If g is continuous, the limit of g of x as x approaches any value I want, and I'll write one in a second, from the left has to be equal to the limit of g of x as x approaches that same value from the right. Again, if you're familiar with piecewise functions, you know the value we're always going to approach is this crossover point where one rule stops and the other rule picks up. So we're going to check this from the left and we're going to check this from the right. Now for this one, what is the rule for g of x from the left? Well, on the left side of 0, that's where we're less than 0. This is the rule on the left side of 0. So we're going to take the limit of 2x squared minus x minus 7. On the right side of 0, we're going to do the same idea, but we're going to use the other function. It's going to be 2x squared plus x minus 7. So when we find the answer to these limits, this one's going to equal 0, this one's going to equal 0. They are going to be the same. Remember, for the continuity definition, I also need to show that's equal at g of 0, but since I've got an equal to sign right here, it is also equal to g of 0. Okay, so this is continuous. Okay, so we know it's continuous. So now let's just reset that piecewise function. Is it differentiable? So the mathematical definition of differentiable you're going to want to use is very similar to the continuous one, except for because it's differentiable, we are now going to work with the derivative of the function. So we're going to ask, what's the limit as x approaches 0 from the left of g prime of x? And does that match the limit as x approaches 0 from the right of g prime of x? And that's what we need to look at. So to do this problem, we got to find two derivatives. We got to talk about the derivative on the left side of 0, Now, the derivative of the left side of 0 would be the derivative of this very first piece right here. So what I'm going to do up here is I'm going to take a moment and I'm going to write their derivatives. So f prime, I'm sorry, not f, it'd be g. G prime of x will equal a piecewise function. The first piece will be the derivative of this top guy. That's going to be 4x minus 1. And that's going to be when x is less than 0. And now we're going to take the derivative of this bottom guy, and we're going to find out that the derivative of that guy is 4x plus 1. And that's going to be when x is greater than 0. Now, you might be wondering, hey, don't I have to include the equal to sign? The answer is we don't know. That's why we're going through this. The whole question is this differentiable at 0? Because that's an endpoint of each of these functions. So we've got to see if they're going to agree. So when I do the limit as x approaches 0 from the left, that's my 4x minus 1. And when I do the limit as x approaches 0 from the right, that's my 4x plus 1. When I take it from the left, I get negative 1. When I take it from the right, I get positive 1. These are not equal, and therefore g of x is not continuous. Okay, g of x is not continuous. And because g of x is not continuous, g of x and f of x cannot be the same function. Okay, so the answer to this question, is it possible that f and g are the same function? The answer is no. Give a reason. F is differentiable. G is not. And with this work, we are good to go. Okay, and to be honest with you, you actually don't even need to do this part. If you could just look at that and realize that these were continuous, you don't need to do this. Just by showing it's not differentiable is going to be good enough to make this work. Okay, we are coming close to the end of time this evening. I want to share a resource with you that I'm going to post in the resources. Okay, I'm just looking at the questions over here. G of x is not differentiable. Oh yeah, I'm sorry. Thank you. You caught that. I appreciate that. I wrote continuous. My mistake. Thank you very much. It's differentiable over here. Okay, I said it in the final answer. I made a slight mistake there. So it's not differentiable. Thank you for pointing that out. So what I want to do now is I want to share with you guys a resource that is something that I actually made up with my students. I'm going to post it in the resources. And it is a table problem that is basically contains every table problem you could ever think of. Okay, here's just a sample of it. Okay, there's actually, I think, 15 parts to this question. I'm going to post it in the resources. It's going to give you guys a chance to look at any type of table problem that they can ask. Okay, and I just want to kind of go over it really quickly with you guys so you can get a feel for the types of things you might be expected to do. This is not everything, but this is some of them. And actually, hold on, I'm going to pull it up in a different spot. If you give me just a moment, let me pull it up here so we can see the whole thing. Okay, so just really quickly, I want to show you the types of questions that they could ask you. Question A, we've already looked at this one, okay? Question A is going to be an integral with U-substitution in it and splitting it up. So it's kind of a really cranked up version of the ones we saw earlier today. Question B, they're just going to test you on the product rule and the chain rule in this one. Are you able to use the product rule and the chain rule? Question C, we already talked about it, doing a Riemann sum. Okay, doing a Riemann sum. Question D, if you guys take a look at this in the resources, and I'll post that there, I'll be there by tomorrow. This is a twist on the problem. You've actually got to use the fundamental theorem of calculus in conjunction with the Riemann sum you just did. So it's combining two different topics. Okay, there will be an answer key posted with it eventually. You can always email me any of your answers, and I can check them for you on the spot. The answer key is being worked on; should be done soon. Okay. How long should it take us to do this worksheet in terms of practice and time? That's a great question. I would say that it depends on the problem. I will make some notes on it when I post it, and then I'll give you guys kind of a general idea, so you'll have a good idea. Okay. But again, please reach out to me with any questions about this sheet. This is something that I made up over this past weekend for my own students, and I think it's going to be really important getting people ready for the AP exam. So if you're working through it, you're not going to find this online. You're not going to find this on Khan Academy or anywhere. The only place you're going to find it is with our resources. So please reach out to me if you have any questions directly. I'll be sure to help you out with it, okay? Question E, again, just to kind of show you what's going on here. Here's that equation of the line problem again to estimate. Question F, find the slope of an inverse. Okay, so slope of an inverse is another question. Question G and H are both related to the mean value theorem, kind of like the one we just saw. Question I, again, estimate by using a 2-point slope. Question J, you're looking at this one, and this is a question that's going to require you breaking out L'Hopital's rule. And L'Hopital's rule is probably going to be on that exam somewhere, okay? Question K, very similar to the problems we've been seeing this evening, just practicing that integrating. Question L, if you don't realize it right away just by looking at it, this is a related rate problem. And then you're going to notice, and this goes hand in hand with one of the questions on the side, okay? These questions here are all asterisks. These are all BC calculus. So if you're in AB, stop after that related rate problem. If you're on BC calculus, keep trucking through this because you've got 4 more questions to look at. And this is where the Taylor series are going to come in. By the way, if any of you guys are in BC calculus tomorrow night, 9 o'clock, Taylor series, okay? So I would strongly recommend if you're a BC Calc student to get in there tomorrow night because we're going to be talking about Taylor series and how they're going to be on the exam. And I am quite confident we're going to see the Taylor series. So please join us tomorrow night at 9 o'clock. We're going to do a session on the Taylor series. And again, M and N are both Taylor series. O is average value, so you have to integrate again. And then P is an integral, but it's an integration by parts problem, okay? So this one question really tests so many different parts of calculus. I'm going to share that with you. You'll see it on the resources. I hope to have it up there later on this evening. So I apologize for some of the difficulties we've been having tonight. I will post my slides. I will post this worksheet at some point, maybe not right away, but we'll get an answer sheet up there. You guys have my email. Reach out to me for anything. We are in this together for the next 2 weeks. 2 weeks from tonight, we'll be at home relaxing because the exam will be over. You'll have taken it on that day. So I'm just going to browse the questions real quick, and then we're going to wrap up for this evening, okay? Let's see. Because we have 25 and 15 minutes for each question, can we have a question like this? You're not going to get a question with this many parts, okay? This is just a review question to make sure you can cover everything in calculus that's related to tables. I would bet, though, with that 25-minute question, we're going to see probably a 6-part question, okay? I would not be surprised at all to see a 6-part question with that one. And on the 15-minute question, my predictions are we're going to see 6 or 7 parts on the first question, and on the second question, we're going to see 4, okay? So that's kind of where I'm getting my kids ready. I think I have answered all the questions here. One more thing, and let me just kind of close out of this real quickly. One more thing I want to make clear to you guys, and I want you to keep this in mind. This is important for the day of the exam. They have written this exam to be long. They have written it so that students are expected to run out of time. So when you're working on that first question and the 25 minutes are up and you've got 1 part you didn't get to, or maybe even 2 or 3 parts you didn't get to, don't hang your head, don't give up, because it's expected that the majority of students will not finish these 2 questions. So I'm just trying to keep your spirits up. If you find yourself doing that first question and 25 minutes is up, just make sure everything you answered is correct, okay? Don't worry if you ran out of time for the last one or the last 2 or even the last 3. Stay strong, go into that second question with a good attitude and work hard, because I am going to bet that 90 to 95% of students will not finish these questions. And that's part of the plan in writing the exam this year. So I really, really want to make sure you guys are aware of that, okay? I see a question here. One of the Fiveable session instructors mentioned that we should not be using union when it comes to stating intervals. Instead, when we were asked to list the intervals with commas, what should we follow? The instruction said they got this from a table leader. Here's the deal. They're pretty lenient on the union notation. So if you don't use union and you use commas, you're fine. You're not going to get into trouble at all, okay? This is in regards to how the question is asked. If you're asked to list intervals, listing means commas. Okay, that's not union symbols. Listing means commas. If you're asked to find the domain, for instance, that's saying give me the union. Tell me the set that you're doing. However, here's the deal. Commas work for both. Commas are safe. If you always use commas, you don't have to worry about it. Unions, if you use it for the domain question, you're right. If you use it for the list, you could be marked wrong. So they're just trying to tell you to be safe on this, and I agree with their sentiment, okay? So commas are safe all the time. You can never go wrong by using the commas. So I hope that answers your question. I got a few more minutes. If you want to stick around and ask me anything else this evening, feel free. If not, a little bit of feedback on how things went tonight. And again, I apologize for the difficulties I had, but I'm glad that we were able to get things up and running and we were able to work together tonight. I hope to see all of you guys tomorrow who are in BC, and then everybody back here on Thursday night for AB. Just to give you a heads up, we're looking at separable differential equations coming up very, very soon for the AB topics. Matter of fact, I'm thinking about separable differential equations for Thursday night. So if you're planning on doing that, separable differential equations will be where we're headed on Thursday night. So I hope that makes sense to you guys. So thanks for your feedback. It's great seeing all you guys. I feel like I'm getting to know a lot of you guys, seeing you so many times throughout the week. But if you're all set, have a great evening. Feel free to reach out to me on email. But I'll see BC tomorrow night, and I'll see AB on Thursday night. Okay? Have a great night, everybody.